So for parts B and C of your performance exam, part B will consist of questions like 9 and 10, and you will be expected to do one of those. And then part C will consist of a question like number 11, and you must do that one. No choice on part C. So again, part B will be examples like 9 and 10. So for number 9, we are working with a linear programming problem. And if we read all the way through it and get to the end, because it says maximize the profit, I know that this is the problem where I've got to write down my constraint. I've got to go to Desmos and graph and find those points and plug those points in to find my answer. So as we read through this question, I'm going to take some notes. So the first thing I'm going to do as I start reading is identify my variables X and Y. This Willy Wonka's Chocolate Factory produces everlasting gobstoppers. I'm just going to abbreviate EG and Monka bars. They make $20 per case of everlasting gobstoppers and $35 per case of Monka bars. That's going to make up my objective function. This is going to be the function that we're trying to actually maximize later. So $20 for every X, 35 for every Y. Right. Then it takes 4 machine hours to make, this is production of the candy requires machine hours and handwork hours. So I'm just going to label this up here, machine and handwork hours, and kind of make like a little table. It takes 4 machine hours to make gobstoppers and 5 machine hours to make Monka bars. It takes 5 handwork hours to make gobstoppers and 10 handwork hours to make Monka bars. The company can dedicate a maximum of 410 handle over 410 machine hours and a maximum of 700 handwork hours to produce the candy. And now we're going to kind of put this all together and determine the number of each type of candy that can be produced. So I'm going to use my notes that I just took to write my constraint. So one of my constraints will be my man hours. So I'm going to do 4x plus 5y less than or equal to 410. And then I'll do the same thing for the handwork hours. 5x plus 10y less than or equal to 700. And then because nothing in the problem talks about that we can't have negative gobstoppers or Monka bars, I need to do those general constraints and say that x and y cannot be negative. They have to be greater than or equal to 0. So those are my constraints. And I'm now going to go to Desmos and graph so that I can find my vertices that I would then plug into my objective function. So Desmos graphing, we're going to type in the 4 constraints that we just wrote, 4x plus 5y less than or equal to 410. And I'm going to use that trick about making everything the same color. I like red really because it's the first color choice. Use whatever your favorite color is. And then we're going to look and see what our shaded region is. We may need to zoom in a little bit so we can see it. So there I can see that I have this little quadrilateral there. Again, because we're maximizing profit, we're not going to use 0, 0. That would be a waste of time. But we have 102.50 as a vertex. And then this one, just outline that dark area, 40, 50, and 0, 70. So I'm going to use those 3 points that we see here. And you're just outlining that dark area right there. And then that's what we're going to plug in into our objective function. So if I plug in 102.5, comma 0 into that 20x plus 35y, I'm going to get $2,050. Then we plug in 40, 50. That will give me a profit of 2,550. And then if we plug in 0.70, we get a profit of 2,450. So then that tells me that there's my maximum profit. So we should make 40 of the gobstoppers and 50 of the Monka bars to get a maximum profit of $2,550. And again, you would need to show all of that work. It'll kind of just be like a previous problem you've seen on the test before, where you'll have blanks for what are your variables, what are your constraints, the objective function, list your vertices and show what values you get, and then ultimately what is your final answer. So then if you don't like that one, then check out number 10. The number 10 is a matrix problem. If you read through it all the way to the end, it does ask us to write a system of equations to represent the problem, write and solve a matrix equation to determine your actual answer, the number of baskets on each side. So the club at our school decided to sell fruit baskets to raise money for a local charity. The club sold a total of 80 fruit baskets. There were 3 different types. We have small, which I'm going to call X, and how much they sold for, medium, which is my Y, and large will be my Z. I'm also told the club took in a total of $2,086.25 and sold twice as many large baskets as small baskets. So if we have 3 variables, X, Y, and Z, we need 3 equations. My first equation is just going to be my total. So total number of baskets was 80, and that total was made up of small, medium, and large. My next equation will be the money. The small was $14.75, medium, 25, and large, every large basket, $32.50. And then my third equation is going to be the twice as many large baskets as small baskets were sold. So twice as many large baskets as small. That means the number of large baskets that were sold was twice as many as the small. So here's my system. And then now I'm going to take that and make it into a matrix equation. So my matrix equation is just pulling out the coefficients. So I have 1, 1, 1, 1575, 25, and 32.5. And then for that bottom equation, and you've got to have all of your variables on the same side. So I'm going to move the 2x over by subtracting it. That's going to make z minus 2x, or if we kind of wrote it in order, it would be, put the x in front, so negative 2x and a positive z equals 0. It is also possible to subtract the z to the right, and then that would be positive 2x minus z equals 0. Either of them will work just fine. So if I moved my x over, that means that my x is now negative. I don't have a y, and then my z is 1. So we call this our coefficient matrix. And then we have our variables, x, y, and z. If we were to do matrix multiplication on these 2 matrices, it would get us back to our system of equations. And then over here, these are our constants, or our answers, 80. 2086.25 and 0. Then to get Desmos to help us out with this one, we're going to go to Desmos. We're going to call this A. We're going to call this B. And then our magic equation, what I always call the magic equation, is A inverse B will tell us how many small, medium, and large baskets we need. So now this is where you're going to pull up your matrix calculator. And then we're going to do new matrix and type in the A matrix. I want it to be a 3 by 3. So click on rows and columns and bump that up. And then new matrix, I'm going to call it B. This time it needs to be a 3 by 1. So make sure you adjust those dimensions. and then just hit enter to get to a new line. And I'm going to do A inverse B. I like to use the buttons here, A, and then the inverse key, B. So that tells us that our answer would be 15 small, 35 medium, and 30 large. Small, 15, or medium, large. And again, part C will be a question like number 11, where there is no choice. We do expect you guys to all do this one. So looking at our rational functions that we just kind of finished up with, we're going to go through and do all of our stuff. I'm going to kind of explain it the same way that I did this for seven review. I like to start with the horizontal asymptote, because the horizontal asymptote, you don't need to do any work. You can look at your original problem. So for horizontal asymptotes, you want your degrees to equal. So when I look at my problem now, I have x to the first power on the top and x squared on the bottom. Well, let's make both of them x squared. So put a 0 x squared on the top, because that still works like not having an x squared. And then on the bottom, there's a 1 in front. And then if you can make the degrees match, or if they already match to begin with, your horizontal asymptote is always going to be y equals the top number over the bottom number. So 0 over 1 is 0. That means that our x-axis is actually an asymptote. We cannot touch the x-axis. And so when I go to do my x-intercepts, I should see later that I'm not going to have an x-intercept because it's an asymptote. All right, now we're going to do our vertical asymptote and holes. So for those two, you do need the problem factor. Top doesn't factor. The bottom becomes x plus 5 and x minus 2. So start with the hole. The hole is the part that you would take out, that you would kind of cancel out. So if we were simplifying this, we would take out the x minus 2. So that means that x equals 2 is a hole. And x minus 2 is the factor that the hole comes from. Set it equal to 0 and solve. Now let's go ahead and figure out where the hole actually is. So we know the x coordinate. It's the 2 that we just got. To figure out the y coordinate, you are going to write down what you get when you simplify. So the x plus 5 on the bottom. Everything went away on the top, so you put a 1 on the top. And we're going to plug 2 into that equation. So that would be 1 over 2 plus 5. So my hole is going to be the 0.217. So if I go over here to my graph, go over to 2 and just go up a little bit. 1/7 is kind of close to 0. My graph, I know that's not perfect. It's kind of hard to get real close to 0 on this phone. Right, now your vertical asymptote is going to be the factor on the bottom that you didn't cross out. So my vertical asymptote comes from x plus 5, but it will be x equals -5. Vertical asymptotes and horizontal asymptotes are dashed lines that I would expect to see on your paper. Now, once you have those three things, go ahead and do your domain and range. And domain is what your x's can be, but it's easier for rationals just to say what they can't be. Well, you can't have x equals 2 because it's a hole. And you can't have -5 if it's a vertical asymptote. So if you're looking at your graph left to right, those are the two x values that won't work. It's when the bottom is 0. And then for your range, think about what kind of y values you're allowed to have. You can have any y value but 0. You can't have a y value that's your horizontal asymptote. Then when we do our x-intercepts, normally your x-intercepts would be looking at the numerator and just setting the numerator equal to 0 after you take the hole out. Well, when I took the hole out, there was nothing left. So since there's nothing left, there's no x-intercept, but also because the x-axis is your HA, you cannot touch the x-axis. Then for the y-intercept, that's when you plug in zeros for all of your x's. If you go back to your original equation and you put a 0 everywhere you see x, or you can actually use the 1 over x plus 5 version too. If you plug zeros in, you're just going to be left with -2 over -10. -2 over -10 would be 1/5. You, again, look over here at 1 over x plus 5. If you put a 0 right here, that just gives you 1/5. Whether you do it in the original or the simplified, you should get 1/5. So then when we go and graph that, I'm going to try to graph this a little bit better here. See if I can make this x-axis hit the, sorry, the H8. Hit it a little bit better. Again, 1/7 and 1/5 are the kind of 2 points that we're looking at. 1/7 is going to be really close to 0. 1/5 is about 0.2. It would just be a little bit higher. And so from there, I could then, if I needed to use Desmos, go and use Desmos to see that I should have a curve going this direction. Skip over your whole, and then 1 over here on this side. Just a rough sketch going out to your asymptotes. And then your end behavior is your HA. Notice on this particular example, we did not fill in the left-right part, so you should do that. So this is saying as I go to the left, as I go to the right, doesn't matter which one is first, but both of those ends are going to your HA. So they're going towards 0.